Okay, in this video we want to take a look at how our dynamic memory allocation actually works. So if you've got this heap that you're maintaining and requests are coming in for chunks of space and to release chunks of space, how do we actually make that function? So I want to look at the layout of memory first, the kind of data structures that we're going to use and what kind of information we have to store with these chunks of memory. And then in the next video, we'll look at the algorithms to actually carry out the allocation and deallocation. So our objectives, we want to give each application its own unique virtual memory space. So it's space that's separate from everybody else. Within that space, we want to make it possible for the application to carve off sections of that to give to, say, threads or child processes that it spawns. So I've got my big space and I want to be able to give this child process a piece of it so that my child processes aren't messing up with each other's data or with my data. With each chunk of memory that we actually allocate, so for each response to a request, or for each chunk of free memory that's available to be grabbed, we want to keep some administrative information. You know, is it free or is it in use? How big is it? Who's using it? There might be all sorts of different flags and bits of information that we want to keep track of. So we'll take a look at that over the course of this video. And we need to maintain some data structures to actually organize the free chunks so that when a request comes in, we can quickly find one that's of a good size, remove it from the free pool, give it to the application, and then when it comes back, when the application's done with it, we want to be able to return it to the pool somehow. And again, we want that to be reasonably efficient. So we'll take a look today at how we might lay things out to accomplish that. So we're going to have three basic levels of data structure here. We're going to have arenas at the top level that are the, if you like, the big overall umbrella container for our pool of memories, or our pools of memory. Then within that, we're going to have heaps that are, if you like, a subdivision of this. And within the heaps, we're going to have chunks that are the pieces that are actually sitting there, either available to be given out or that are currently in use by the application out there someplace. So the application, when it fires up, will be given one kind of top-level arena that controls all the memory space for that application. Within that, it's going to have its memory stored as a heap divided into chunks. The arena has the ability, if it needs to subdivide that heap into smaller heaps or even into smaller arenas. So for instance, when if the application spawns a child process, it might carve off a piece of its memory and turn that into a small arena that it gives to that child process. So the child process thinks it's got an arena all of its own, and it's just taking up this chunk of space somewhere from within the parent arena, if you want to think of it that way. And then the heaps themselves are going to be, some chunk of memory or some big block of memory that's divided into chunks. Each of those can either currently be free or allocated to some application. We can take the chunks as we need to and subdivide them. So if I've got, a 5 megabyte chunk and the user only needs 1 megabyte, maybe I can carve off 1 megabyte at the front and then have the 4 megabytes that's left over as a separate chunk. So we can subdivide these things. Or if we have a couple of adjacent free chunks, we can join them together, coalesce them together into a single bigger free chunk so that we can handle bigger requests if one comes in. So the heaps are kind of looking at this idea of divvying things up into chunks and allocating them, deallocating them. And usually we're going to try and arrange our heap so that it kind of fills from the bottom up. So more or less as requests come in, we're allocating them at the bottom of the heap. And we're keeping this one great big free chunk at the top of the heap in case big requests come in case requests come in that are too big to handle with any of the little free chunks we have that we've already carved off. So we've got our arena, we've got the heaps within it, and then within the heaps we've got these chunks. So these are the pieces that are actually allocated to a program or that are freed up by a program. So for your allocated chunks, right, if chunk has actually been given off to a program somewhere, to an application somewhere. Obviously, it needs the space that the program asked for. So if they asked for 4 megabytes, it's got to have the 4 megabytes. But we're also going to have some administrative information to support how we actually do our memory management. So there's going to be a little bit of overhead on top of what the user requests. And the same idea with the free chunks. Once the user has, or once the application has released a chunk of memory and it goes back into our pool, we've got to have information associated with it, right? The size of it, the fact that it's free, and a bunch of other administrative bits and pieces that we'll talk about in just a moment. Usually, this kind of administrative info is going to be either at the beginning or the end of the chunk, so that if you've got a pointer to the chunk, or you know where the chunk ends, you can quickly find that administrative information. And then the big whack in the middle is going to be either free, or just totally unused at the moment if it's a free chunk, or the application is going to be doing something with it if it's a chunk that they've actually requested. So I want to look at those two sides independently. What might we store with an allocated chunk, and what might we store with a free chunk? So the administrative information for an allocated chunk, at the beginning, the overhead stuff that we'll have is the size, something that says, okay, this chunk is 2 megabytes, or this chunk is 64 bytes, or whatever it might be, how much space it takes up. We'll have maybe a byte that specifies which arena is actually controlling this chunk. We might have a byte indicating if this is a specially handled chunk. So when really, really big requests come in, requests that are too big to handle with our ordinary mapping system like this, if we've got if the user makes a request for something that's really too big for us to effectively handle within our heap, then we'll send a request directly off to the operating system, memory map request. So those will be handled as a special case. So we'll have a flag to indicate if this is a special case or not. And then we'll also have a flag to indicate if the chunk right before this one is currently free or not. So, this might be set to true if it's free and false if some application is using the chunk before this one. And the idea is, when this chunk gets released eventually, we can look at that flag and say, if this chunk is now free and the chunk before us is free, I can merge them together into one bigger free chunk. So this flag is particularly useful in the deallocation process. And then, of course, there's all the content, the space that the user is actually getting. And the pointer that the user gets back might actually be to the start of this space. And then for the other side of things, for the chunks that are currently free, that aren't currently in use, again, we've got to have a bunch of administrative data. There's going to be a big whack in the middle that's just this whole mass of unused free space, that we're just waiting around to give out. But at the ends of it, we're going to have some more information. Again, we'll start off with the total size of the chunk. We'll start off, or we'll follow that with, again, a flag indicating which arena is keeping track of this. A flag indicating whether or not this is memory mapped. I think that should be false if this is currently free. We'll have, again, a flag indicating if the chunk right before this is free or not. And there are going to be points, there's going to be some intermediate stages in our deallocation algorithms where some of this information is temporarily needed. And then we're going to have pointers to the chunk before us and the chunk after us, referring to kind of the previous free chunk and the next free chunk, so that I can, if I need to, kind of wander through my chunks of free memory in a linked list sort of approach, a doubly linked list approach, I guess. So we can see where the previous free chunk is and where the next free chunk is. And then after the big whack of kind of unused empty space, we're going to have the size again. And the idea is, if I'm sitting on one chunk of memory and it gets freed up, and I want to, I look at the flag in it that says the chunk before me is free, then I need to know how big that chunk before me is, right? I don't know where the beginning of it is. So if right before me is the size of the chunk that's before me, I can figure out where the beginning of that chunk is, and I can find my way to all of this information. So for the free chunks, we store the size at both ends. So that's essentially the data, the information that we're keeping track of with our chunks of data. And in the next video, we'll see how we use that information to carry out our allocation and deallocation.